Hello, now that we have this qualitative understanding of the Wilson renormalization program, right? And we understand that what is happening is that as we coarse grain, as we go away from the ultraviolet degrees of freedom, we're moving through the space of equivalent Lagranges that encode the same physics, at least as far as the infrared of these theories is concerned. Right? Now what we want to do is to get a more systematic and generalizable way of calculating the running of these constants. Right? And we start by realizing that these two expressions that we got in the very last part of the previous video, right? They have a similar characteristic, right? What you can notice here is that on one side, the running, right? So this is the value of the coupling constants for these two theories, right? Lambda phi 4 in a massless lambda phi 4 theory in 4 and less than 4 dimensions, right? This is the value of the coupling after one renormalization group transformation, right? With a finite size given by b, right? B here is between 0 and 1. Closer to 1 than to 0 if you want to make this a small step, right? But we have two things influencing how far lambda prime will be from lambda. On one side, you have the perturbative expansion, right, which says that this correction is small compared to the leading one, right? And on the other side, there's also the size of this step, right? We see that in both cases, unless b is really close to 1, in this case, it's really clear that if I try to take b to 0, this log will explode, right? Which is a big step in this case, right? And in this case, if b is not really close to 1, unless this parenthesis here is really small, right, then the correction will be proportional to lambda, which is my UV scale, which is supposed to be big, right? So in both cases, these corrections can become quite large in the limit where b is much smaller than 1, right? And that seems to work in the opposite direction of lambda. So I have to be careful with taking big steps here in this version of our renormalization group, right? This problem with the big logs, there's also a log disguise here, right? Also appeared when we were calculating the photon self energy, right? So we got this expression, let me repeat it here, for the photon self energy. So this is what I called pi of q squared, right? And at one loop, this was given by the following expression. Let me write it here. Still in terms of Feynman parameters in this case, because we can see what we need here. M squared minus x, 1 minus x, q squared. And of course, there's contributions of order alpha square. So that's what you get at one loop, right? And that led to running for the charge, right? So we could plug that in some effective value for the coupling of the theory, right? Which was given by this expression. And then if you plug that in and take also the ultra-relativistic limit, where we can take the mass of the electron going to 0, right? Then this becomes just alpha over 1. So if I take the mass to 0, I can ignore that term and do the integral easily, right? And that becomes alpha over 3 pi log of minus q squared over m squared exponential minus 5 right? So there's still a mass here, not taking exactly the mass to 0, just saying that the mass is much smaller than minus q squared. So I can take that away, but I still have a dependency on the mass there. Right? And that's the expression we used to calculate the Landau pole, right? So you can see that even if I keep this fixed, right, I choose some renormalization condition so that this guy is just 1 or very close to 1 over 137, right? So it's a small number. Still, the effective thing can become quite large if q squared is very big, right? If I take, I go all the way to the UV, right? So that makes clear that that depends on the value of this external momentum. What is not totally clear here is that that also depends on the position of this reference point, like a Q0, that I'm using to define this 1 over 137. And in this case, I used Q0 equal to 0, right? So let's make this a little bit more explicit. So what we want to do is to generalize the renormalization condition we used for QED. Right? The first time we did this, right, we used this renormalization condition for the photon self energy. Now we want to make this a little bit more general and just leave this as some unspecified scale Q naught, right? So if I impose my renormalization condition like that, there will be a few changes to the process that we use to calculate this guy. In particular, you have to go back to the video where we did this and take a look. The first thing that changes is the counter term, right? Now we are making this change. The counter term will become this one, because essentially I have to make the counter term conceal the pi 2, which is just a one loop contribution at this point, right? So now it will be calculated at q naught, right? And the counter term becomes a slightly different expression. So this is in dimensional regularization, so I have the diverging part of the dimensional regularization regulator, right? This is the divergence, and then you have the usual mu to the square that includes these logs of 4 pi and whatnot, and this is where the change enters, right? Now I have m squared minus x 1 minus x q naught square, right? Which of course goes back to what we had before, just put this part to 0, right? This is of course more general. And that means that this pi of q that we have up here, now we'll get a new piece, because this numerator of the log was exactly this part, right? When you subtract, when you do pi 2, which is just the one loop contribution, minus counter term, this part with the mu2 that goes away, and you get the log of these over that, right? So now this will be the more general version, will be this. Let me rewrite it. Now we have pi of q squared, as a lot of these is similar. Let me copy. Forgot the limits of integration. You should know that by heart at this point. And then there's a log, of course, with two terms here, which are fairly similar. One is this, right? And the other one is the actual dependence on the external momentum. So you see how this goes back. And of course, there's corrections of higher order in alpha. But you see how this goes back to the one we had, when you take Q naught equals 0, right? So now we can go to the ultra-relativistic limit and remove them. Electron masses, also assuming that I'll fix this reference point somewhere in the high energy limit, right? So now pi of Q square will be just minus alpha over 3 pi, because this integral contributes with a 1/6 here, and the logs become really simple. It's just Q square over Q square, Q naught square over Q square, right? Which means that the effective fine structure constant becomes just alpha. Again, it's the same expression here, but if I substitute these here, I get alpha over 1 minus alpha over 3 pi log of Q square over Q naught square. Right? So now it should be pretty clear, right, that not only this has it's the Landau pole still here, right, but it's not just for high Q square, right? The thing is, if Q square is too far away from Q naught square, that's where the divergence happens, right? In fact, you could think, well, then there's a trick I can do, right? I can go as high as I want in Q square, as long as I keep choosing higher and higher Q naughts as reference, right? That way that log is never big. But that's just an illusion, right? Because what's happening is that this guy is now not, right? This guy is different from 1 over 137. Of course, the physics should be independent of the choice in Q naught. And that means that if you choose higher and higher reference points, you could use the expression at lower reference points to calculate how much this guy needs to be there in order to have the same physics. Right? So this, if you keep increasing Q naught to keep the log under control, what will happen is that this reference value here, this constant, which has an implicit, right? This is again not really a constant, right? This has an implicit dependence of Q naught because this is defined, right? In fact, this constant, quote unquote, right, is defined as the value of alpha effective calculated. At this point, right? So if I keep changing Q naught, I change alpha with it, right? And it should increase, in fact, to give the same Landau pole in the same place, right? So what that hints at, right, is that the size of the logs is being compensated by the value of this constant, so that the actual dependence on Q square, which is the external momentum, right, is unchanged, because this is something I can test, right? The alpha effective is something I can test more directly, right? And the hint here is that probably instead of doing a series in alpha, right, and truncating for some power of alpha square, right, my parameter of expansion should really be alpha effective and not alpha, right? So that's the first hint we get from these calculations, right? But we didn't formalize that. Everything we did so far was really using alpha as an expansion parameter. So those logs were not under control, right? So that's the first point. Another related point is how these logs are appearing in this expression right here. If you remember, the way this pi, which is the 1 pi contribution, right, comes to the denominator like that, is through a resum of a geometric series, right? I could rewrite this alpha effective in the form of something like, there's this alpha right here, right? Times 1 plus some coefficient. I won't worry about these numeric coefficients here, right? But the point is there is an alpha and a log, right? Alpha, log, right? Then another one, the next term will be alpha square log square plus then something else like alpha cube log cube, right? And so on. And that whole series, right, comes from the sum of one loop diagrams here, because pi is the whole sum of 1pi diagrams, but I only calculated pi at one loop to get this expression. So essentially what I'm putting here is a sum of terms that look like this, right? Let me make this a little bit smaller, right? So this is this term, right? This next one is something like this. And let me make this one also a little bit smaller, right? And the next one is something like this, right? That's where this alpha log to different powers come from, right? I'm just resumming this infinite tower of contributions of one loop, right? And schematically, I can write this contribution in this way, right? So alpha effective is behaving like alpha times this external alpha here, a sum of n bigger than 0 of alpha log of q square q naught square to the power n, right? This is what is appearing in this infinite sum right here, right? But the thing is, when I do that, I'm including alpha to high powers, right? Alpha square, alpha cubed, right? And we know there are two loop contributions that also have this order. In QED, the next one would be this one, right? This guy is, you see, there's 4 electric charges here, so it's e to the 4th. That means this guy is order alpha square. And again, these wiggles here means I'm ignoring the numbers, right? There's the factors of pi and whatnot, right? But I'm only really worried about this alpha and the logs, right? So this is not really the usual perturbative truncation of my series. I'm not truncating already to get this expression. I didn't truncate at order alpha, right? These two, of course, are exactly the same in the limit where I can disregard alpha square, everything, right? Then I'm just writing this expression, but I'm really just thinking of this, which is true rigorously for very small alpha, right? And nothing else, just writing this, and I send it to the denominator just by assuming this is small. But of course, things complicate if I want to go to order alpha square, right? Because now I didn't include this two loop contribution, right? And this in fact is known as the leading logarithmic resummation, right? A leading log approximation, sometimes you hear it, right? Instead of the perturbative truncation. Now this sounds a little bit absurd, right? You could think that this guy is the same order of this one, right? But there is a sense in which this series can be understood, right? So let me just try to show you. Suppose I do now the same thing, but for the two loop contribution. Let me make these two guys smaller, otherwise I won't have space, right? Suppose now I do actually a similar sum, but for these guys, right? In which situation disregarding now the sum of two loops in comparison to the sum of one loop diagrams is acceptable, right? It would be acceptable if I could prove, right, that this sum is actually very similar to this one, but with alpha square here, right? Because in this case, now I have this common factor to both sums, right? This and this, right? But this is suppressed by an extra power of alpha. So in that sense, I could make this leading logarithmic approximation, right? The thing is, I didn't show this, right? And in this case, it's not obvious at all that I couldn't, at some point in this series here, find for instance, a term like, say, just for the sake of the argument, something like alpha cube log square. In that case, I have, if you see, if I factor alpha square in front here, right, I have something where the powers in alpha and the powers in log are not the same, right? So my series now is not just in terms of this basic element, which is alpha times the log, right? So I have different sums here, and then I would have to go to the details, right? So it's not obvious to anyone by doing this process we did. We went to one log and just resummed it, right? But it's not obvious that these things won't appear, and they don't, right, in this series, right? They don't in this series. So we want some method that, if this expression would really be true, that would give us this expression like that without resorting to throwing away these diagrams. And we'll see if we can get anything like that, right? We could, in the case of QED or lambda phi 4, we could in principle calculate the two loop contribution explicitly, right, and show this. But that's of course a lot of work and not doable in general, especially if you go to complicated theories, right? It's not very practical to do two loop calculations in theories with many couplings, right? And of course you would have to go to three loop and prove the same, and that's of course not very desirable. So we want something more efficient. All of these problems point to the same, or at least hint to the same solution, right? So the size of these steps in the renormalization group transformations clearly show us that maybe we should try to define this better in some continuum limit, where I'm walking through this renormalization group continuously, right? Also, this relation between the definition of alpha here and this reference point, this interdependence between these variables, right? Especially when you have variations in variable, you're trying to match the variation of one variable with the variation of another one, also hint of a very usual solution in physics, right? Which is differential equations, right? Both the continuum version of the renormalization group and this are pointing to the fact that we need to write these in a more sophisticated way than trying to do discrete steps, right? Trying to fix the constant here, see a finite distance to it, and then if we need fix it somewhere else, and then see another finite distance. Maybe we should do these more smoothly, right? And the thing is, in the last video, we actually we have proven this, right? That the Wilson coefficient, this is limited to the scalar theories, right? With n scalar fields and m derivatives for the operator. And we have seen that under a discrete step, right? This is how the Wilson coefficients change, right? It's not hard to turn this into a differential equation. Let's see how we can do that, right? So if I take B, remember the continuum transformation would be to take B arbitrarily close to 1. So let's define a variation of B away from 1 in this way. So I'm defining this delta B, right? Where delta B is very small number, but it is positive, right? So that when this goes to 0, B goes to 1, B goes to 1, and I have a very small transformation, right? Remember that this B that was left over in the Lagrangian, right? Because we did two transformations last time. It's important to be careful. One was the integration out of the UV degrees of freedom with a parameter B, right? And then after that, I did a rescaling. I just stretched my space-time by the same parameter B. That's when B showed up in the Lagrangian, right? In the Wilson coefficients. So this B here is really the scale transformation. And under that scale transformation, momentum scales were contracted, right? I said that K prime was K over B. In particular, that also tells me that under this transformation, anything with dimension of momentum, including the cutoff, right, will also scale in that way. So when I do that scale transformation, I'm stretching the cutoff, the effective cutoff for that theory under these new coordinates, right? And because of that, I can now rewrite, right? I just substitute this expression for B here, right? And I have that lambda prime is approximately 1 plus delta B, because I'm bringing this to the numerator, right? Lambda, which I can write in this way, right? Lambda plus lambda delta B, which now defines my delta lambda, right? I can call this little piece here delta lambda, right? So this is how lambda transforms, lambda plus delta lambda, right? And then just comparing these two, I get one of the expressions I need, which is that delta B corresponds to delta lambda over lambda, right? And now what can we do? We can go back to this expression and use these definitions, right? And write this thing, right, in this way. Let me just move this to the right a little bit. I just put 1 minus delta B right here. So this is to this power, right? Which then I can approximately write as, right, C and M. There's a minus here, minus here, there, right? So this will be just plus the dimension of this Wilson coefficient times delta B times C and M, right? Which again defines my delta C, right? This is the variation of the Wilson coefficient. Oh, in linearly, I'm taking everything linearly on the variations here, right? Because I'm thinking of this limit, right? And so now I can use this last expression here, right, to write delta of the Wilson coefficients in terms of delta B, right? What I'm seeing here is that delta C and M, right? Just take this equation, take delta B and divide on this side over delta B is equal to these other two things here, the dimension, C and M, times C and M. Now I just have to replace delta B by delta lambda that I have from here, right? This becomes just lambda delta C and M delta lambda is equal to this. Make that white. which immediately gives the differential equation I wanted, which is that lambda dCnm, now really taking the limit, right? The lambda is equal to the dimension of Cnm times Cnm, right? So you see, this is a very special case of something that is really general. A differential equation that tells me how one quantity in my theory, in this case the Wilson coefficient, changes in terms of an unphysical parameter. Remember, the cutoff in this Wilsonian approach is just something that is really far away, and our observables should not depend on this cutoff, right? So I found a differential equation for the relation between these two things, the Wilson coefficient, which impacts directly our observables and low energy, and the cutoff, right? This is pretty much the way all the renormalization group equations work, right? In fact, I could more formally get this kind of differential equation, but actually demanding, right? I could start from the fact I choose some appropriate observable, right? And I demand that this is true, or in other words, that this observable does not depend on the cutoff, right? And if I then develop this properly, I'll get differential equations just like that one, right? In fact, this is not the only option, right? This is in the Wilsonian approach, where the cutoff is the unphysical parameter, right? But you could do also this in other schemes, right? We know that we'll probably not use these very much because this hard cutoff that you introduce in Wilson renormalization breaks Ward-Takahashi identities, and that's not good, right? But you could also do the same thing, right? In terms of that, remember when we did Pauli-Villars, or we choose a renormalization scale, we choose to do the renormalization conditions at a specific scale, which we call P naught, sometimes U naught, S naught, Also, our physics shouldn't depend on that, right? Even worse, if you go to dimensional regularization, right? Or even in the MS bar schemes, there are many different things that we call mu, right? Some cases was just this parameter that we put to compensate dimensions in the dimensional regularization. In other cases, mu was the subtraction point for MS bar schemes. This is all unphysical, right? And these conditions should also be true, right? So you see, by different choices of which parameter I'm using here and which observable I put here, right? What object, not necessarily an observable either, right? As long as I can make the case that this object that I put here does not depend on these unphysical parameters, then I get a differential equation that should look like that one, right? Of course, you could ask, what is the usefulness in that, right? How does that help us? I mean, to find how my coefficients depend on unphysical parameters, when I'm really interested in how they depend on physical situations, right? Especially the external momenta going in when I'm doing an experiment, right? To see the relation between those two, let's look again at the photon self energy, right? Again, we did calculate the photon self energy a few times, even in exercises, and we have seen that at one loop, what the expression we use for it is this, right? And pi 2 here means just the loop contribution, right? Just that vacuum polarization diagram. And delta 3 is the counter term, right? And for dimensional regularization. This turned out to be given by this expression. And that's before we choose a renormalization scheme. So we have some freedom to choose now. Right? This is 2 over epsilon plus log. This is very similar to something we wrote today already, but now I'm not imposing any condition still. So the counter term will still be here explicitly. Let me write the whole thing, q square, plus some numeric constants. So you might notice I took out the tilde from here, because that depends if there's a log of 4 pi, there's an Euler-Mascheroni constant, all of those numbers I'll just call const here, right? But that thing can change from equation to equation. It's just all the numbers that do not depend on the external momenta nor on these unphysical parameters that I'm putting here, not, at least not explicitly. There's no mu, there's no epsilon in there, nothing, right? And of course there's no counter term. This thing I wrote here is just the one loop diagram, right? Again, let's look at the ultra-relativistic limit, just because it's simpler to see stuff at that limit, right? Then I can disregard this mass here and do the integration. That gets easier. This becomes just minus alpha over 3 pi, 2 over epsilon, plus log of mu square minus q square, plus this thing. We changed from this equation to this one, right? It's another number, but I don't care too much what it is. Because of course, there's always this minus delta 3 here that can absorb these numbers or not. So of course, if it depends on the choice of delta 3, it shouldn't matter physically, right? So now this expression, let me put a box here just because we'll compare many different versions of this. Right? This is in dimensional regularization. I still didn't choose a renormalization condition that will fix my delta 3, right? If I did the same in Pauli-Wieler's, right, the expression I would get at this point is this one, pi of q square, same calculation, different regulator, right? 3 pi log of lambda square over q square, right? Plus different numbers, right? Depending on how you do this calculation, is even 0, but in general, you could have numbers there, right? So this is what you get in Pauli-Wieler's. PV. And keep in mind, this lambda now is not the cutoff in the Wilsonian approach. Is really the mass of this Pauli-Wieler's ghost particle, right? So you see, you have a lot of these parameters going around, and you have to be careful which ones are which in each version of this calculation, right? The point I want to call attention to here is that in this ultra-relativistic limit, right, there's only one physical scale which has dimensions of mass, right, which is really this fictitious lambda in this case, or this mu here, right? These unphysical parameters are the only mass scales in the ultra-relativistic limit. That means that if I get logs of these constants, right, they will always also be this dimension of these constants inside the logs will have to be compensated by the only physical scale of the problem, which is the external momentum in this. This is a propagator, right? This is just something like that. There's a Q going in, right? And that means that if I find the coefficient of this log of the physical parameter, right, I will also have found the coefficient of the log of Q square. And this connection between these two, right? If I solve the differential equation for this guy, the dependency of any, in this case it's a green function, right? If I solve for the dependence of this green function on mu, automatically I'll get the dependence on Q square, right? You could say, what about the if I go away from the relativistic limit, right? Then I know that the mass must appear summed with Q square somehow, combined, right? Of course, there's constants in the middle, but the mass must appear in a combination with the external momenta. Otherwise, this thing I just showed here wouldn't be true in the ultra-relativistic limit. I could not have something like that, because then I would have no ultra-relativistic limit where I could disregard the mass. I would have the wrong dimensions here. So if you do the dimensions carefully, you see that finding the behavior of these constants, or at least the log of them, will also tell me how the log of the external momentum is working, right? And there's more to it, right? There's two different things we could do here. One is, which is the most, I would say, the most intuitive renormalization condition, and the least intuitive renormalization condition. So the most intuitive one would be, say, I'll use some scale, right? Some physical scale here. Let's say I take pi of Q square at some point Q naught square, right? Say this is 0, this is a renormalization condition, right? And that's, in principle, is a measurement. I could measure alpha, right, by using, say, I don't know, a scattering, when this guy is essentially the photon exchanged in a process like that, right? And I could measure the potential or the charge. We know that the whole effect comes from this, right? And that would fix my Pauli-Wheeler's counterterm, right? In that case, I combine this equation, the Pauli-Wheeler's version, with this condition. I get my delta 3. In this case, delta 3 would be just minus alpha over 3 pi log of lambda square over Q naught square, right? And then I substitute that here, right? Do the subtraction, and my pi of Q square becomes minus alpha 3 pi log. I'll leave the signs here just so we don't lose track of them, but I have signs on both the numerator and the denominator in this case, right? Plus constants, of course. Cannot forget the constants. I could choose to eliminate them with delta 3 or not, right? And in this case, I think they will go away, so this is probably 0 with that condition, but that's not my point, right? The point is that this expression is probably the one people have least problems with. In principle, you say, if I choose Q naught and make a measurement at that scale, right, with Q square, the external Q square, the same as Q naught, I'm essentially measuring alpha, right? And that defines alpha at that scale, and everything is really understandable, right? But now let's compare this with the least well understood renormalization condition, which is the MS bar. Seems really like really arbitrary thing, right? In the MS bar, what I do, MS bar is done in the dimensional regularization, right? And the MS bar tells me I just throw away this 2 over epsilon and the log of 4 pi and the Euler-Mascheroni constant that are inside here. Right? That's all I do. So essentially, what I'm saying is in the MS bar, which is applied to the dim-reg version of the function, right? I'm choosing my delta 3 to be just minus alpha over 3 pi, right? 2 over epsilon plus the log of 4 pi minus the Euler-Mascheroni constant, right? In this case, pi becomes, I just have to subtract up there, right? It's really simple. This one is really simple operationally, right? It's just minus alpha over 3 pi log of mu square over minus q squared. You see, always these things depend on some arbitrary constant, right? In this case, q naught, in this case, mu, but it's much more intuitive for us to understand what is q naught, is some reference scale, right? Then this mu that started in the dimensional regularization just as something to compensate the dimensions of the constant, and then in the MS bar we reinterpret it as a subtraction point. So there's very little to tell us what physically, I mean, is this constant, right? But the thing is, they seem very different, but you have the same expression, right? And this is not a coincidence. The thing is, I could easily make another one, another condition. Let's call that yes, I don't know how to pronounce that, right? Which stands for yet another scheme. And in this case, I just choose delta 3 to be minus alpha over 3 pi 2 over epsilon plus the log of mu square minus q0 square, which is just a number, right? This is arbitrary, this is arbitrary. I can just choose a combination of the two, right? And I apply that to dimensional regularization scheme, right? In that case, what I get, right, if I go to the dimensional regularization, subtract, I'll get exactly this expression, right? Just go there and check, right? The moment I subtract, I'll do away with mu and replace it by q naught, right? And also eliminate the 2 over epsilon, which is the only thing I really have to do to have a finite quantity, right? Now, you see, this is exactly the same as just taking this MS bar scheme and identifying, just say, oh, he reinterpret mu as the reference scale, right? In this case, I'm taking this minus is just because I want to be always in the Euclidean part, right, to avoid branch cuts and whatnot. So I'm taking mu squared to be positive and q naught squared to be negative, right? So that's the minus. But other than that, I'm just reinterpreting mu as the subtraction point now is the same as the reference scale, right? The point here is that it doesn't matter, right? These constants, even when they seem like they are physical here, right, they are really not. I mean, no measurement should depend on this choice. So these are numbers that we like to interpret a lot, right? And they really don't mean anything, right? You have to be careful that your observables do not depend on these parameters, and that's exactly the fact that the observables don't depend on them is exactly what we can actually explore to get the physical dependence, right? So what we'll do from now on, we will just give up on all these parameters that have already names and feelings associated to them. And now I'll just call this arbitrary scale m square, right? And everywhere it matters, I will concentrate on, I will do the calculations in Minkowski space, but I'll stay where in the region where q square minus q square is bigger than 0 and m square is bigger than 0, right? Because then we stay on the part of the calculations where you have, first of all, this is more useful to look, that's the situation where you're thinking of T and U channels, so scatterings and potentials, right? Instead of pair production of particles, which have a more complicated analytic expression, because once you hit a certain threshold, you start producing real particles in the middle here, and that's a complication we don't need to understand the renormalization group equation, right? So now I want to write everything in terms of this m square, and m squared can stand for any of these constants. It doesn't matter because the behavior will be the same. All I'm doing is throwing stuff back and forth between this logarithmic dependence on the external momenta and a bunch of constants that can all be absorbed, if I want, in the counterterms. The only thing, and this is very important, in fact, the only thing that cannot ever be absorbed in the counterterm is this log of q square, right? Because this would be, in a Lagrangian, the log of a derivative, right? Square times times some operator, right? And this is a non-local term. So if you're talking about a local Lagrangian with local counterterms, the log behavior is the only thing that cannot be absorbed in the counterterms. So we must encode the whole physics of the problem. So that's these log variations is really what we're looking for, right? And in that case, I can take any renormalization scale, right? That's how we call this guy generally. It's just the renormalization scale in terms of which I'll write a differential equation. With that in mind, let's see the first example of a renormalization group equation, which is the so-called Callan-Symanzik equation. And in this case will be RGE, right, a renormalization group equation for a green function. So let's start with a green function. We have in mind here a scalar theory with just one field phi, which is a simple case, and we'll also assume pretty soon it's a massless one, so we can look at the coupling, right? So the green function will be given, right, endpoint green function will be given by the expectation value of a time-ordered product of fields, right? And I'll use a little index here, 0, because I want to start with the bare green function. What means bare here? Means I didn't renormalize my theory yet, right? So this could potentially be a diverging quantity at one loop. I don't care. I'm just talking about the green function before I did any renormalization. And this can be written as this right here. So the time-ordered product of n scalar fields, right? And these are also the bare fields. So I put a 0 to the fields themselves to differentiate these from the renormalized field once I redefine it of a factor z, right? So we have n insertions of this field here in n positions that go from x1 to xn, right? So for now, right, really this equation, right, this expression is totally independent of this renormalization scale M, right? Because I didn't renormalize my theory, M shouldn't appear here anywhere, right? Now, once I renormalize my theory, doing the usual thing, right? I define a field phi given by z to the minus half of this phi, not the bare field here, right? Now I have a new green function, which I can write like this, right? Phi of x1 all the way to phi of xn omega, right? So the vacuum of the interacting theory, okay? And so this is now what I'm calling Gn of x1 to xn, right? Xn. And this is related to this previous green function by this transformation. So I can just write this as z. Since I have n fields on the right side, right? This is just z to minus n over 2 times this expression here. Right, let me just shrink it a little bit. I delete this guy, makes it nicer looking, right? So now I found a relation between the Gn, right, and the Gn bare, right? And the thing is, I can now demand, right, that the G0n dm is equal to 0, because this guy does not depend on this renormalization scale, right? And we can use that to find a differential equation for this guy, because they are related, right? So let's do that explicitly, right? So what happens here is that when I go from G0n, oops, to Gn, right? I'm changing a lot of things, right? When I do the renormalization, I'm not only redefining the field, I'm redefining a lot of constants. So say this is a scalar theory that can be a complicated theory with many couplings, right? You could have a lambda, a m0, I don't know, maybe there are fermions there too, and I have a Yukawa coupling, some electric charge, you name it, right? You could have all of those things, and you're just calculating the green point function for the scalar part of the theory, right? So this theory could depend on all of that, and I'm using the 0 to represent the bare constants, right? This depends on the bare field, right? You have to use it to calculate, and it might also depend on a cutoff, depending on how you start. If you're starting a la Wilson, then you have a finite cutoff somewhere. If you're doing like in the BPHZ approach, then this is infinity, right? You could have a cutoff or not. The point is that after renormalization, right, you now have the constants have been renormalized. You define some lambda, a physical mass or renormalized mass in the MS scheme, some couplings, right? You exchange the field for just a renormalized field, and also you won't have the cutoff anymore, because that being finite or infinite has been subtracted through the counterterms, and now you have a dependency on M. So this guy really depends on M, this one doesn't. M can be anything, remember, it could be mu, could be Q naught, it could be any of those scales. And of course you could do that again and again, right? You could do that for different conditions and have here a G prime that depends on my lambda prime, M prime, G prime, everything defined at a different M prime scale. So the moment you change your definition for M, your value for M, everything else changes, right? But the thing is, all of these renormalized green functions, if I multiply them by z, if I take this one and multiply it by z prime to n over 2, and I take this one and multiply by z n over 2, both of them need to be the same as this one, right? So you see they are all related to G0, and the only thing that changes when I change M is really this Z here. That's an important thing, right? In the case of the green functions. So I can ask myself, now I want a differential equation, right? I can ask myself, just like I did for the Wilson coefficients, right? What happens when I do something like that? I go from some M to some M prime, right? But I'll take M prime to be really close to M. So this is M prime, right? And I'm just doing a small change in M, right? In order to get a differential equation. In that case, everything changes. Now I'll specialize, right? Let's take a theory where all these parameters are 0. So I have no mass, no other couplings. It's just a lambda. We can even later specialize for lambda phi 4. I have just one coupling and one field. So in that case, lambda will go to some lambda prime, which I'll write like that. Again, a small variation. And the field will transform like that, right? But keep in mind, this is a definition that what is hidden here is really the variation of z, right? Because this initial field, let me write that on the side here, I have some initial field, which is defined in terms of the bare field, like that. And the new one, this one on the right, will be defined like that. So you see, I'm defining the value, instead of defining a delta z, I'm calling this delta eta, but this, I could get delta z from here, right, if I wanted. I just have to write delta z in terms of delta eta, right? But this is more practical for us right now. So now the green function, as I have written up there, right? The green function in the renormalized theory is just z to minus n over 2 g n 0. Let me remove this dependency on the position because that does not help us in any way, right? And since this is independent of m, right? That's the main condition we're using here. Never forget that really what we are doing is demanding this is 0. So that's where this enters, right? That means that all the change in G comes from Z, right? So when I take this definition for Z, how Z changes, right? Z goes from this to this as I change the renormalization scale. That means that Z to the power n minus 2 will go to 1 plus delta eta, right? To the power n. I'm just taking this relation and raising to the power n, right? Z to the n over 2 minus n over 2. Which then I can linearize because delta eta is supposed to be small, right? I'll take all these variations to be small, right? And that means this is approximately 1 plus n delta eta, right? Z and 2, right? And now that means that the variation of G, right, is coming only from this part. This is a constant in terms of M, right? And that means that Gn goes to 1 plus n delta eta G of n, right? That's the important part. It's all coming from this Z that is in front of G0 in both cases, both before with M and after with M prime. Never forget that this is my M prime, this is my lambda prime, etc. Right? Now, if I think of G as a function, right? The G is a function. The renormalized G is of course a function of these positions, right? X1 all the way to Xn. But really, in terms of these variations, it is also a function of M and a function of lambda, right? There's a coupling in the theory, only one in this case, and this guy depends on that coupling. Right? That means I can write the variation of G, dg, n, as the partial derivative. Now I'll try, usually my partial derivative, my derivative, they look just the same. In here I'll try to be a little more exaggerated on the d's here so you can see that. So this is really the partial derivative of Gn in a straight explicit dependence in M, right, times the variation of M plus the partial derivative of G with relation of the coupling, right? There's two things it can depend on, right? Times the variation of lambda, right? And this one needs to be the same at this small part here, right? Since I already concluded that the full variation of G is just this piece, right? This is Gn plus dgn, right? So dgn here is this part. So I can write that this is equal to n delta eta Gn, right? And now I got my differential equation. It's already here, right? I just have to do some massaging to put in the format everyone uses it, right? That's essentially just now defining some useful things that show up here. The first one is I like to rewrite these two pieces in terms of this piece and this one, in fact, in terms of very important quantities. So first, I'll define something called the beta function. If you ever heard anything about renormalization before, you heard about the beta function, right? And this will be defined as m times delta lambda over delta m, right? This is the beta function. And I'll also define something that for now we'll call just a gamma function. Later we'll find a different name for it, but for now that is it, minus m delta eta delta m, right? So see the delta lambda is here, the delta eta is here, so we can easily make these two things appear, right? Just take this equation, let me rewrite it in this way, so I can take this piece down here, take this one, bring to the left with a minus sign, so this guy comes over here, and that means this whole thing is equal to 0, right? And now I just take the whole thing and divide by delta m. So I just multiply on both sides of the equation, delta m, and I also multiply m in the numerator, because you see how I define these things, right? So now I have the equation I wanted, right? Let me write this. So this delta m goes away, because I multiplied this big, right? I multiply by this, so here I have m times this. In this piece, I get, let me just copy this part, right? And I have multiplied by m, and I have delta lambda delta m, right? Here's the same. I have minus n m delta eta delta m g of n. I feel like, no, there's a g here, there's a g there. Okay, I didn't lose anything, and this is all equal to 0. Right? Now I can identify these guys, right? I have the beta function right here. And I have the gamma function right here, including this minus sign. The gamma function is here, which allow me now to rewrite this as a differential operator acting on G. Right? Let's write this explicitly like that. M, I have to be careful with my M's, they don't always look that good. Right? Partial derivatives plus beta function, partial derivatives now in the coupling, right? Here I just have plus gamma, there's no derivatives, n gamma, right? There's an n there, which is the number of external legs in this green function. And this is acting now on Gn, which I can write explicitly to remember that this guy is a function of all these positions, but also, once I renormalize my theory, right, of these two guys, and notice lambda here is the renormalized coupling, right? Now we can do some thinking on beta and gamma, right? You can see that my definition of beta and gamma is totally independent, right, of n. I could do this equation, everything I did up to this point, for any n-point green function in this theory, right? And so both beta and gamma are independent of n. I'm just trying to see what these guys could depend on. In principle, they could depend on n, they could depend on the renormalization scale, and they could depend on, I don't know, the coupling of the theory, right? I'm already concluding here by the way I'm doing the calculation that this does not depend on n, right? Also, by dimensional analysis here, you see that these three terms in the parentheses here, in these brackets actually, right, are adimensional, right? Here I have mass over mass, so this term is clearly adimensional. The other one should too, right? Should be adimensional too. This is a number, just the number of legs, right? So that means gamma is adimensional, and beta is also adimensional because lambda I'm thinking about a dimensional coupling here, right? Lambda 5,4 essentially, right? So beta is also adimensional, and that means since there's no other scales in this theory, remember I'm talking about a massless theory, that means that beta and gamma cannot depend on this renormalization scale either, right? They are just dependent on the coupling, right? Which allows me to finally write these more explicitly, right? Just so we remember what beta and gamma are all about, right? Beta is a function of lambda. That's what this means now, right? Same for gamma. And now we get what we wanted, which is the Callan-Symanzik equation, right? And keep in mind, this is totally equivalent. In fact, we could have just have done derivatives from this equation right here. If I imposed this equation on G naught, right, equal to 0, that means I'm demanding that my bare green function does not depend on the renormalization scale, which is trivial. This multiplication by m is just to make the right functions appear here, beta and gamma, right? And in fact, I'll give an exercise to get here straight from that equation, right? And now you will see, right, that you can actually see in the definitions of these guys, right, that beta is encapsulating really the running of the coupling constant. You see what happens here, what appears here, is really how the coupling constant changes when I change the renormalization scale, and gamma is encoding the change in the field. Remember, eta is the way I decided to encode the change in the field renormalization constant, right? And the field strength, right? Renormalization. So gamma is encoding this change in the field normalization. Now you could have done this to more complicated theories, right? This is in fact, very easy to generalize. For instance, in the case of the massless QED, we will attack masses later because masses can be a little more complicated. But in the case of the massless QED case, the equation, or the Callan-Symanzik equation, would look something like this. So you have a beta function for the charge, right? And the partial derivative on the charge. And now you have two fields, right? You have a gamma for the electron. It depends on the charge, right? And another field renormalization related gamma for the photon field, right? They are called gamma 3. And of course, those two are related, right, to Z2, which renormalizes the fermionic field, and Z3, which renormalizes the gauge boson propagator, right? And all of that apply to G, right? Where now my green function can have these two numbers of external legs, right? N tells me how many electrons I have, the fermions, and M tells me how many photons I have, right? Green functions in QED can depend on these two quantities, right? And then the rest is the same. I have the positions here, and of course the renormalization scale and the charge, right? And the derivation is very similar to what we just did, right? But now you since you start with two z's in front, right? Essentially your G will be proportional to Z2 to some power, right? Minus n over 2, and Z3 to minus m over 2 G0, right? You have a change in this part, right? This part is the same. Instead of lambda, I have the charge, right? Nothing changes. And so see how similar and how easy it is to generalize these for more complicated theories. You could also have more than one interaction. Same would happen with these beta functions. You would have more than one beta function, right? So now there's a few steps we need to take, right? In order to solve this equation, we need to know these functions. We need to know beta and gammas, right? And once we know betas and gammas, we can plug them here and solve these fairly complicated differential equation, right? So do that in steps. Next video we'll go to the problem of calculating betas and gammas. In fact, most of the calculations are already done, right? It's should be intuitive that these functions are generated once we have loops, and we already calculated one loop contributions to both lambda phi 4, right, which is what I have in mind here, and QED. Right? So we have the loops already calculated. It will be easy to relate them to beta and gamma. And then once we have that, we'll go and solve these Callan-Symanzik equations. So that's the subject of the next few videos. See you then.